My name is Nicholas Makasis. I'm here with my colleague, Monica Kreitmeyer. We're researchers at the University of Cambridge, and today we'll be talking to you briefly about our work involving modeling of the subsurface and understanding how heat flows through it. The motivation for our work is the need to decarbonize the heating networks within cities. We believe that geothermal is key for achieving this, as it is a low emission source of both heating and cooling. It is immediately underneath dense urban centers, which is close to where the demand is, and is also available throughout the year. In order to determine the capacity of the ground for heat extraction, rejection, or storage, and to understand the environmental impacts large-scale deployment of ground heat exchangers can have, we need large-scale models. And that is because the ground is a continuum, and therefore temperature anomalies can be transported further afield through groundwater flow and conduction. However, as models become larger, they also become more expensive, to the point where they can be infeasible to run. So we have been working on developing a methodology that can rapidly create a temperature map of the ground underneath UK cities. And having the temperature map, we can then assess the capacity of the ground to provide geothermal solutions. In this work, we use numerical modeling as well as machine learning techniques to identify common behavior in heat transport phenomena within blocks of land. And this is based on natural features such as hydrogeology, as well as anthropogenic features such as human-made infrastructure within the ground. And identifying this common behavior allows us to minimize the modeling very significantly. We have applied this methodology to two boroughs in central London, the City of Westminster and the Royal Borough of Kensington and Chelsea. And we're going to share with you a snapshot of how things work.
Right, so in this application to central London, we are including heat sources that are specific to the area. So for example, the exact basement location, as well as the presence of the London tube network. And we can then go underground and calculate how the heat flux from these is transported within the previously mentioned predefined blocks at any depth to get the temperature distribution at a large scale. And here we are looking at how temperature changes over time at 20 meters beneath the ground surface. And we can clearly see the effect of the tube network heating up the surrounding ground. And as mentioned previously, this also presents a greater capacity for shallow geothermal to be used for heating. And so what this does, it allows us to build a more holistic pictures of the thermal climate underground, and how this then changes with the use of the ground through the building of new infrastructures, such as deploying ground heat exchangers. And ultimately, what this does, it helps us create a more sustainable pathway to decarbonizing heat networks within urban centers, through the tool coming out of this, allowing us to understand better the impacts of large geothermal deployment and to regulate it better, which then allows us to use it more effectively because we have fewer unknowns that create barriers to deploying. We can use it more equitably because we can deploy the ground heat exchangers with less thermal interference. And so we get lower diminishing returns by avoiding something of a thermal tragedy of the commons. And ultimately, we also have a lower environmental and ecological impact by better informing regulation. So if you found this interesting, please feel free to contact us. We'd be very happy to talk about it.